Okay, now let's introduce projectile motion. And what projectile motion is if we have some particle or some ball or a bullet and it shot up with an initial velocity and it shot has a initial angle, we'll call that theta. It goes in two different planes. It goes into our y plane, which is up and down, and it goes into our x plane, which is left and right. And it's going to have an initial position of y naught, and an initial position in the x plane of x naught. So this position is x naught, y naught. And if we look at this initial velocity, it's shot at some angle, and it has an initial velocity of v naught. So its velocity in the x direction is going to be its x component, which is v naught times the cosine of its angle, the angle it shot at. And that's right here. And we can do the same thing in the y direction. So its initial velocity in the y direction is going to be equal to v naught times the sine of theta. Now, if we think about this and we shoot a projectile, we know it's going to go up to some maximum height right here and then fall back to the ground, and at some point it's going to hit the ground and stop moving. And how do we analyze any projectile motion problem? Well, we have to see that the force acting against this is going to be gravity. So our acceleration is going in the negative direction, so it's going to be gravity. And typically, gravity, if I put it where you can see it, gravity is going to be minus 9.81 meters per second squared if we're using metric, or 32.2 feet per second squared if we're in English units. So how do we describe, what's the equations we use to describe this type of motion? Well, what we need to do is we need to break up this problem into its horizontal velocity and its horizontal components and its vertical components. So if we look at its horizontal components, we are going to use the kinematic equations. And these kinematic equations are an final velocity is equal to an initial velocity plus acceleration times time. A final position is equal to an initial position plus an initial velocity times time plus 1/2 times the acceleration times time squared. And a final velocity squared is equal to an initial velocity squared plus 2 times the acceleration times a final x position minus an initial x position. And we're going to use these equations twice, once for the horizontal components and once for the vertical components. And we will have our equations we can analyze projectile motion with. So if we look at this equation, our final velocity in the x direction is going to be equal to our initial velocity in the x direction plus an acceleration times time. And this acceleration, there is none. There is no acceleration in the x direction. Acceleration is gravity, and acceleration is only working in the negative y direction. So this goes away, and we have a final velocity in the x direction is equal to the initial velocity in the x direction. So this means the velocity never changes in the x direction. The x component of velocity stays constant throughout an entire projectile motion problem. Okay, and if we look at this third equation, we will find the same thing. So the velocity squared of the final velocity squared of our x component is going to be equal to the initial velocity squared of our x component plus 2 times the acceleration of our final x minus our initial x. And again, there is no acceleration, so this term goes away. And both these equations say the same thing, that the initial x component of velocity is equal to the final x component of velocity. So if we look at this final equation, this equation right here, we have our final x position is equal to our initial x position, and we can see that with this example right here, that it doesn't need to be 0. It could be 0, but it could have some initial x position plus the initial velocity in the x direction times time plus 1/2 times the acceleration times time squared. And again, this term right here goes away because there is no acceleration. So really the only equation of any consequence in the horizontal direction is this part of the equation, that a final x position is equal to an initial x position plus the velocity, the initial velocity in the x direction times its time. Now, since acceleration is pointing in the negative y direction, when we look at these vertical equations, we're going to get more equations we can work with. And we're going to simplify it up a bit. But if we look at this first one, we have the final velocity in the y direction is equal to the initial velocity in the y direction plus the acceleration times time. And we said acceleration is gravity, and we can write this as the velocity in the y direction minus gravity times time, and this can be our first equation for our vertical component. Now if we look at the second equation and we just change the variables up a bit, we have a final y position is equal to an initial y position plus the initial velocity in the y direction times time plus 1/2 at squared. And again, we know a is gravity, and it's pointing in the minus direction, so we have y naught plus the initial velocity in the y direction minus 1/2 gravity times time squared. And this is our second equation. And our third equation will be the final velocity in the y direction is equal to the initial velocity in the y direction squared plus 2 times the acceleration minus the final y position, or times the final y position minus the initial y position. And if we simplify this up, we get the initial velocity in the y direction squared minus 2 times gravity times the final y position minus the initial y position. These right here